Hey everyone, and welcome to this explainer. I am absolutely thrilled you're tuning in today because we're about to dive into something most of us use literally every single day. We are going to unpack the sheer, mind-blowing mechanics behind what I like to call the celestial compass. We're going to bridge the gap between that comforting little blue dot on your smartphone screen and the incredibly complex network of satellites constantly zooming around the Earth above our heads. Trust me, the engineering precision required just to keep you from missing a turn on your way to a coffee shop is absolutely wild. So let's get right into it.
Okay, picture this. You've just stepped out of a subway station in a massive, bustling city you've never been to before. The buildings are towering over you, the streets are this total maze of one-ways, you have absolutely no clue which way is north, and honestly, a little bit of panic starts to set in. But then, you pull out your phone, you open your map app, and boom, there it is. A glowing blue dot showing exactly where you are and exactly which way you're facing. It's an instant wave of relief, right? We've all been there. We rely on that blue dot without even giving it a second thought, treating it almost like magic.
But, that brings up a really fascinating question. Think about what is actually happening in that exact moment. How on earth does a hunk of metal orbiting in the freezing, completely empty vacuum of space thousands of miles away know precisely where you are standing down on the ground? It's tracking you down to a few meters, right through the clouds and the atmosphere to a specific street corner. How is that kind of pinpoint accuracy even possible?
Well, here's a wild little secret. Most of us have kind of bought into a myth. If you ask people how GPS works, they'll almost always say, oh, it's triangulation. We hear it in spy movies and TV shows all the time. But actually, scratch that. It's totally incorrect. GPS doesn't use triangulation, which is all about measuring angles. Instead, it relies on a completely different mathematical concept called trilateration. So, what exactly is trilateration? Simply put, it is the process of figuring out a specific location by measuring distances, not angles, using the geometry of intersecting circles or spheres. That's it. The entire global positioning system is based purely on figuring out exactly how far away you are from specific, known reference points up in the sky. It is all about distance.
To visualize this, let's just imagine a simple, flat 2D map. Think of it like a giant puzzle. Step 1, your phone figures out its distance from satellite A. That gives us a massive circle on the map, meaning you could be anywhere on the edge of that circle. Step 2, your phone finds its distance from satellite B, drawing a second circle. Where those two circles overlap, we now have two possible intersecting points. You've got to be standing at one of those two spots. Finally, step 3, we bring in satellite C and draw a third circle. That third circle is only going to cross through one of those 2 points, and boom, that single unique intersection, that is exactly where you are.
But, of course, there's a catch. Let's scale this up to reality, because that three-circle analogy is great for the math, but we don't live on a piece of paper. Our world is in three magnificent dimensions. We've got towering skyscrapers, super deep valleys, high-altitude flights, and winding mountain roads. Intersecting flat circles simply aren't enough to track you in a 3D world.
Which brings us to the magic number for GPS, 4. In a three-dimensional space, satellites aren't drawing flat circles. They're projecting massive 3D spheres of distance. When two spheres intersect, you get a perfect circle. When three spheres intersect, you narrow it down to 2 points, one of which is usually way out in deep space, and the other is somewhere on Earth. But to establish a true, highly accurate, totally guaranteed position, you absolutely need a minimum of 4 satellites locked in, no exceptions.
So why is that fourth one so absolutely crucial? Because it secures your definitive 3D spatial reality. It locks in your latitude, how far north or south you are. It locks in your longitude, how far east or west you are. And incredibly importantly, it locks in your altitude. Without that fourth satellite's intersecting sphere, your phone might think you're standing on the sidewalk when you're actually at the top of the Empire State Building or cruising in a commercial jet. 4 satellites are the bare minimum to give you that perfect 3D blue dot.
But hang on a second. This pushes us right into the core engineering challenge of this whole setup. We know GPS relies on measuring distances, trilateration, to draw these massive intersecting spheres. But how exactly are those distances being calculated? There isn't some giant tape measure dropping down from orbit, right? The satellites aren't bouncing physical lasers off your phone. So how on earth does your device know it is exactly 12,540 miles away from a specific satellite?
Well, the absolute secret ingredient, the beating heart of how this entire system functions, is time. That's right, GPS is not actually a distance measuring system at its core. It is, fundamentally, a highly advanced, unimaginably precise timing system. The satellites are just up there broadcasting the time, and by measuring how long that signal takes to travel from space down to your phone, we figure out the distance.
Now, to pull this off, your standard wristwatch is definitely not going to cut it. Radio signals from these satellites travel at the speed of light. If a clock is off by just 1,000th of a second, your location on Earth would be calculated incorrectly by nearly 200 miles. So to prevent your map from telling you you're in the middle of the ocean when you're actually in Kansas, GPS satellites use ultra-precise atomic clocks. These are insanely complex, incredibly expensive instruments that measure microscopic, tiny fractions of a second with just flawless accuracy. So here's how the magic play-by-play actually unfolds. First, the satellite transmits a radio signal that basically says, hey, I am satellite X, and my atomic clock says the exact time is this, down to the nanosecond. Next, your phone catches that signal. Now, because the signal took a tiny fraction of a second to travel through space and the atmosphere, the timestamp on that signal is ever so slightly older than the actual current time on your phone. Your phone calculates that exact delay. And finally, because we know radio waves travel at the constant speed of light, your phone just multiplies that travel time by the speed of light. Travel time combined with signal speed equals precise distance. Repeat that whole shebang with 4 satellites, and you've got trilateration.
It is just this brilliant cascade of technology. Think about it. We go from ultra-precise atomic clocks humming away in the freezing vacuum of space, broadcasting timestamps at the speed of light, down to complex spatial geometry and 3D intersecting spheres calculated in a fraction of a second, and it all translates seamlessly to that simple, friendly, glowing blue dot in your pocket. It's literal cosmic space math distilled down into everyday convenience, just guiding you effortlessly to wherever you need to go.
So, as we wrap up this explainer, I really want to leave you with a thought to chew on. We are entirely, deeply reliant on this invisible net of synchronized atomic clocks flying thousands of miles above our heads. If GPS simply stopped working for 24 hours, no maps, no delivery tracking, no ride shares, no global supply chain logistics, which part of your daily life would be the most immediately and severely affected? It's crazy to think about how deeply integrated this celestial compass really is. Drop your thoughts down in the comments, keep wondering about the incredible world around you, and I will see you next time.